Um, okay, so if you know the law, it's not too difficult to do this. The first one. First rule is that log of A times B is the log of A plus the log of B. You can apply that here. Well, actually I threw a denominator in there, so you have this related law that really isn't anything new. If you have the rule for power. So this rule is really an instance of this. Once you have the rule for power, anyhow, we use these two rules to simplify this. So first of all, we could use the second rule. I'll make myself all right small. Applying the second rule, we have a division here, so we can subtract the two expressions. Okay, you subtract the log of the numerator with the log of the denominator from the log of the numerator. Then we can use the first rule. So let's just number these rules. I'll call this rule 1. I'll call this rule 2. So rule 1 applies to the division. Rule 2 applies that this log is going to be log of 5 plus the log of x to the 6 plus the log of y cubed. And then we still have minus the log of c. Okay, at this point, these rules don't allow us to go any further. Actually, we could. We could write the log of y cubed as a log of y times y squared. You get the log of y plus log of y squared and break it down that way. But the third rule is going to be much handier. Log of a to the c equals c times the log of a. And this is our third rule. And applying that up here, but we still have the log of 5. Then we're going to have 6 times the log of x. Plus 3 times log of y. And then minus 3 times the log of z. And there it is, expanded out as a sum of multiples of logs. Really straightforward with little practice. It's very easy to do. Now comment that these rules are related to the rules of exponents. Remember that the log is inverse functions of the exponent. So in a sense, these rules are inverse to rules of exponents. Remember, your rules of exponents say that I'm trying to decide what letters to use here. don't want to confuse the notation. I'm going to use X's and Y's. Don't confuse the X's and Y's I use here with the X's and Y's, these expressions. Okay. I'm going to use lowercase a's and b's. I'm not going to prove these laws in detail. It's a little bit challenging to understand. You don't really need it at this point. But you know, x to the a plus b is x to the a times x to the b. So that an addition becomes, in a sense, becomes a multiplication. An expression with an addition in the exponent becomes an expression with the multiplication of two powers of x. Okay, here you have a multiplication, and that becomes an expression with a multiplication becomes an expression with an addition. Okay, so here there's an addition. And a multiplication. I'll write that pretty small, I think. Understand what I'm writing. So you have an addition and a multiplication. Here, you have a multiplication. I'll go ahead and put a dot there, just to express the multiplication and an addition. It's not a very deep mystery where these rules come from. If you just apply definition of log and inverse function, it becomes fairly clear. But again, I'm not going to push you to understand that. Now down here, you have an exponentiation that becomes a multiplication. Now, where's an instance where that happens with the rules of exponents? Well, x to the a to the b equals x to the a times b. You have an exponentiation here and a multiplication here. Over here, you have an exponentiation on this side. I don't really have room to write that easily, but I'll abbreviate. There's an exponentiation, and here you end up with a multiplication. I'm not going to say too much more about that, but I just want you to be aware that this is just, these rules don't come out of the sky on a stone tablet. They follow very simply from the rules of exponents, which follow very simply from a few examples. So it's best if you understand the rules and where they come from. On the other hand, I don't think it should be, but it's probably a little beyond the scope of the course that we're teaching to prove the equivalence. I think it ought to be. I'm not gonna push it that far. Okay. And you're probably glad I don't. So it's worth thinking about. It's not a terribly deep connection. So we want to understand that these rules are totally connected to these rules. Okay. Now let's take the second one. Three log x. That's 5 times log y. Well, by the third rule, this is just a log of x cubed minus the log of y to the fifth. And that's by the third rule. And you get used to it, you do some problems and pretty soon you're good at it. Okay, well, we can then apply the first rule. And say, well, this is a log of x cubed over 1 to the 5th. And it's not overly difficult. Again, with a little practice, you get pretty good with this. Okay, so we have this situation. Viscosity, liquid bandage is exponential in time. Look closely, you can see a little bit right under my hand. Okay. The viscosity. Let's be a little clear about what I'm saying. This is in the bottle. Now, there are assumptions around this, like I'm opening the bottle every day or every third day. Okay, but I'm opening the bottle at regular times. Okay. Can you put this information on a graph of viscosity versus time? The information I've given you gives you 2 points on this graph. Okay, everybody did that quite well. The question is how to scale this graph. Okay. One way to scale it is to have 0 here and 12 out here. Now, sorry, 0 here and 40 out here. And 0 on the y-axis, 12 up here, so that your 40-12 point be about here. And that's a perfectly good thing to do. If you do that, though, your graph is not going to show you where the viscosity is 200. If 12 is here, 200 is way up there. However, if you put 200 here, 12 is going to be down really close to the axis, and your graph is going to look really flat. Okay? Now, if I look at what people did, half of you did it one way, half of you did it the other way, and they're both sensible ways. And what it's going to come down to is we're probably going to need to do 2 graphs. One graph to see the short-term behavior of the exponential function from 0 to 40 days, and another then that extrapolates way out past that. Okay, so that's okay. So we're going to put let's start with the local graph, the graph over a small time interval, relatively small time interval. Okay, so we got 40 there, we're going to have 20 here, we'll have 10 here, 30 here. I could divide these intervals up a whole lot more, but actually all we need is 40. Okay, now we need 3 here, and of course if I subdivide the interval from 0 to 12 in 2 parts, looking at this thing up here, tend to get things looking high. Okay, maybe that's good. So 3 would be here, 6 would be here, 9 would be here. And now we can put a couple of points in the graph, and everybody saw that real nicely. Okay, 0, 3 would be here, and 40, 12 would be here. Now, if you didn't draw this graph, don't get rid of the graph that you did draw, but do a quick sketch of this graph and put an exponential function, an exponential curve on it. Okay. Well, to do a good exponential curve, you kind of want to start close to the x-axis, come on up. Yeah, it's not very good, but you get the idea. Okay, going to use that to make a couple of estimates before we go on. Now, the question is, according to the graph that I drew, according to the graph that you, according to your graph, what's the doubling time? Now, by the doubling time, what do I mean? That means the time it takes to go from one value of the viscosity to double that value. Okay, you got that pretty well. Now, I can take any point on this graph. So let's just take this point here. And I can estimate the viscosity. Okay. And I can estimate the time. So if I got a point on the graph, it makes sense to go ahead and estimate its coordinates. So I'm going to say the coordinates here look to be about 7. And 3.7. And 3's read. It might be a little better. Okay. Now that's an unfortunate choice on where to label the point. Looks good until you think about what I'm going to do next. But I think about what I'm going to do next. So I'm going to label it down here. Three came out better that way. Okay. So we're asking how long it takes to double. For an exponential function, it doesn't matter what 2 points or what point we start at. The time it takes to double is always going to be the same. So you start at any point on an accurate graph of an exponential function. Now, this is a pretty inaccurate graph. It didn't come out very well. So we're not going to get a great estimate. But we're also going to be able to figure out what the doubling time is. It's actually kind of obvious when you see it. But according to the graph, okay, I'm estimating 0.7, 3.7. Now, if I want the thing to double, well, the viscosity is 3.7. If it doubles, it's going to be 7.4. Where's 7.4 in the graph? Well, here's 6. Here's 7, here's 8. I'm going to say 7.4 is about here. Okay, so viscosity is about 7.4 on this line. Now I've got a point on this line. It tells me at what time that viscosity occurred. If I project down here, and I say it comes out about 29. So now we've got 29, 7.4 on the graph. So the question now is, how long did it take to double? Well, the time it took to double from here to here. And clearly, that would be the run of a fundamental triangle with these points, okay? But of course, a fundamental triangle between these points to give you the average rate at which the viscosity was changing. It's kind of worth seeing that since it's sitting here smiling at us on the graph, but that's not what we're doing. We're just trying to find what this time is. And the doubling time is from 7 to 29, right? Okay, so there's our doubling time. Now, what's the real doubling time? Now, we had two estimates, okay? Well, people got two different estimates. Okay, the lowest was 20, the highest was 22. Okay, so one of you estimated exactly what I did. And since my estimate was done on a pretty flawed graph, maybe that wasn't the best, but it's close, okay? And it turns out that the doubling time really is 20. So if you estimated 22, that was a good estimate. If you estimated 20, you nailed it. Okay, now how do I know that the doubling time is 20? If we go from 3 to 12, how many times did it double? Twice, right? Okay. You double 3, you get 6. You double 6, you get 12. So here our estimate is 22. The actual, well, one doubling gives us 6, right? One more doubling gives us 12. So 2 doublings in what? If this is days, it's 40 days, right? So I knew not to write this so low on the board, but I'm going to do it anyway. We have 2 doublings in 40 days. So each doubling takes 20 days. And we could see that on the graph as well. 0.6 ought to match up with 20. But it looks like we got the 0.620. These different colors. And then, of course, here we have the point. I don't know if there's a cure. I'm not dyslexic, but I do write things down backwards when I write coordinates sometimes. Whatever coordinate I'm thinking of first is the one I write first. I don't think, many times I don't think about what I'm doing. So it's 26 and 40, 12. Again, From here, we're at 3, we double, then we double again. And each doubling requires 20 units of time, 20 days looks like. Okay. Well, this raises several important questions about an exponential function. If you're given an exponential function, how do you find its doubling time? Now that's coming up. But we actually, now that we've known a little bit about logs, have all the tools we need to determine it. I don't think I want to do that yet, though. I'm tempted to, but I don't think so. Just from where everybody is, I think it's really better just to do this. Okay. First of all, what's the function y equals v of t for viscosity? As a function of time. How do we do this? It's an exponential function, so we're going to have v of t equals a times b to the t. Each point on the graph gives us a value of t and a value of viscosity. Okay. So for example, the point zero 3 on the graph tells us that the viscosity is 3 when the time is 0. So there's an equation. And it turns out that this equation tells you what A is. Usually, unless you have the t equals 0 value, you won't get the value of A immediately. You have to do a little more with the simultaneous equations, but right now we have that. Okay. So what's the other equation you get? What's the other point that we were given? It was 12 at t equals 40, right? We got the point 40, 12. What equation do you get from the point 40, 12? Just rewriting a little bit of what I've written here. What's your equation? Okay, so everybody got this almost immediately. B is 40, sorry, B is 12 when t is 40. So we got 12 equals A times B to the 40th. Okay, now we have a system of two simultaneous equations with two unknowns. If you have one equation with one unknown, then if your algebraic techniques are up to it, some equations they just can't even be solved by any known technique. Okay, but if you have the algebraic technique with one equation and one unknown, theoretically, it's got a solution. Okay, if your algebra is up to it, you can find the solution. If you have two unknowns, you need two equations. In this case, we can easily find A from the first equation. Okay, so let's call this equation 1. Call this equation 2. Equation 1 is equals A times B to the 0, so B to the 0 is 1. And it very quickly follows that A equals 3. Second equation is 12 equals A, B to the 40th. But we know that A equals 3. So we take our value of A, plug it in for A here, and we get the equation. Well, equals 3B to the 40th. And now we can easily solve for B. So that we get obviously we're going to divide both sides by 3. And you get 4 equals B to the 40th. And I'll flip sides here. I'll take B to the 40th and raise that to the 1/40th power. You could also call that 40th root. The B to the 40th to the 1/40th is 4 to the 1/40th. By rules of exponents, why did we do the 1/40th power? Because if you do a power per power, you're going to multiply the powers. If you multiply 40 by 1/40th, you're going to get 1, and that's going to give you B. Well, B to the 1 is 4 to the 1/40th. And I'm going to guess that that's about 1.034. You've got your calculator. So correct me. Okay, well, I have to admit, for the first time in my life, I made a mistake. It really should be 1.035 to something. So we'll cross that out and have your way. Leave your calculator instead of me. But get that thing checked out. There's got to be something wrong. Okay. Okay, so what does this tell us about our model? So A equals 3. And B is approximately 1.035. So what's your V of t function? Okay, y'all are having a good day. Everybody wrote that out almost right away. P of T is A, B to the T. The whole reason we did this is figure out what A is and what B is, so we can write out the function. Well, everybody was on top of that. Okay, and very pleased to see that. Okay, 1.035 raised to the T. Okay, now. What is viscosity after two weeks? How can you use that function to figure out the viscosity after 2 weeks? Now, if you don't have a calculator handy, I don't need to, you have one? Okay, so you can use it. So you can find it out, but write it out on paper first. Write out what you're going to put into the calculator so that you've got a documentation for it. And if you just write it out, you don't really even have to put it in the calculator, but it's kind of okay. So it's optional whether you want to really use the calculator. What I really want to see is the expression. Then the calculator will confirm it. Okay. So everybody did real well. Everybody said, okay, well, 2 weeks is 14 days, so T's going to be 14. So we find V of 14. Now, one way to find V of 14, if you got a good graph, and it really helps to understand the concavity of this graph and everything, to understand the way exponential functions work, because it's going to be close to related to your financial world and other things. I come up to take that turkey to cool off at Thanksgiving. Took out a loan and bought a turkey the other day. They're twice as expensive as they were last year. Still not a bad buy. Okay, so anyhow, we go out here and estimate where 14 is. Okay. Then we can project up to the graph and over. And it looks to me like pretty close to 5, but I'm going to say 4.7. Okay. Now, knowing a little bit about exponential functions, we have a little, and never mind, I'm not going to use that. It'll take you too long and I'll mess it up. Okay, so at least from the graph, I'm estimating 4.7. Now, my graph is a little too flat here, and then it kind of has a kink in it here. So I don't have a huge amount of faith in this estimate. But what did you get? Well, what you put into your calculator is 3 times 1.035 raised to the 14th power. Okay. Okay, so I'm going to ask you in a minute to tell me what you got. Okay, so you get about, I think you said 4.85. So that really rounds off to 4.9. So don't worry about hurting my feelings. I got 4.7. You got 4.9. I'm okay with it. I'm used to it. Now, okay. And so we're learning a lot about how this viscosity changes. Now, if this is money, it'd be really interesting. Okay. You're going to see money examples in the homework. So you don't need me to give you more money examples. Let's see how much this board space I've got. Let's just move everything over a little bit. Okay, yeah, we're good. I can actually come back. All right, now I could ask you to find the average rate of change between two t values. Okay. Everybody feel comfortable doing that? If not, review what the average rate of change is. If I'd ask for the average rate of change for the third week, which starts on the 14th day and ends on the 21st day, then you would evaluate this at 14 and at 21. And you get something like a little over 6. And then you'd have a triangle between this point and this point, and have a rise and a run. And you divide the rise by the run, and you get the average rate of change, because rise is a change in viscosity. Change in viscosity is how far you go this way from the 14th day to the 21st day. Go from here to here. You got to rise, that's your change in viscosity. You got to run, goes from here to here. 14 to 21, it runs 7 days. So you get a certain change in viscosity per day. And that's your average rate of change. It's an average rate of change because the rate of change actually keeps increasing. So it gets steeper and steeper. Slope keeps increasing. And look, those are important characteristics. When you get to calculus, that's really kind of the crux of what you spend a lot of time studying. Okay. So I'm going to go ahead and address the half-life. Rand is fired again. The doubling time, this is decreasing, it's increasing. Actually, you could say that half-life is negative, which means the doubling time is positive, but let's just do it a simple way. I really like to write it out in general, but we're going to say time for V of t to double. Just say at t equals 0, v equals 3. So the doubling time, which I'll write as t dub, sub dub there, sub dub. Makes me want to create a nursery rhyme or something. But anyhow, t dub is when the value of t is the value of t when v equals 6. Well, can we write this out as an equation? We don't have a lot of time. I don't want to constrain you at this later point in class. I'm just going to say, so this means we're going to solve v of t dub equals 6. Now, if we write out what v of t dub is, well, v of t is 3 times 1.035 to the t, so v of t dub is 3 times 1.035 to the t dub. So v of t dub equals 6, just says that 3 times 1.035 to the t dub equals 6. Okay. What's the first thing you're going to do with this equation? We don't have time for me to have you work it out, but I'll bet you can. We have 5 more minutes, we do it. So, well, if we divide both sides by 3, I don't have room to write it out. We know if we divide both sides by 3, we're going to get 1.035. The T dot equals 2. Okay. Now what do? I think we did this last time. I know we, well, yeah, this is make sure. And it doesn't hurt you to see it again because you will kind of get used to it. Okay, so we convert this to the logarithmic expression using the inverse function property. Okay, and I know we did this last time because I've seen it in your notes. Okay, I don't know if we worked it out, but I kind of think we did. Okay, so first place, we convert this to the logarithmic notation. This is an excellent, your T dub is in your exponent. Your T dub in this case is your exponent. And other than using the inverse function idea, there's no way to isolate that T dub. The only way you can isolate it is to convert this to the equivalent logarithmic expression. Okay, so I want to get used to that. I don't really need an arrow. And then I told you how to calculate log to base whatever of a number. That's just log of 2 over the log of T dub. Of 1.035, using the rule that log V of C equals log of C over log of V. Okay, the rule that you have, it's an easy rule to apply. And it's what you do at the end when you get a log to a weird base of some number. Okay, so calculate this. What's log 2 over log of 1.035? Okay. Okay, so one calculator gives a little bit of a curveball. One calculator actually has a way that you can enter just this expression. Okay. Log base. I want you to do it like this with the straight LOG key or the LN key. For at least, I mean, you can use this if you want, but I'm going to want to see it documented at this step. So you're probably better off taking the extra step and do log of 2 over log. Anyhow, you get something like 20.14. Now we know from what we did before that the doubling time is exactly 20, right? From the initial information, we figured that out. And from your estimates, that's very plausible. So how do we get 20.14? Well, that 1.035 was rounded off. Is 1.035 to something. Okay. So this comes out just a little bit different because we did have to round off the 1.035. Okay. But there you have it. And that comes nice full circle. This addresses most of what you need to know about exponential functions and some of the techniques that you have to use.